and see what we can accomplish. Okay, what we have done so far is talked about the concepts of equilibrium, chemical equilibrium. If we have a reaction going to products, it will go so far and then will stop and reverse itself. This is referred to as a dynamic equilibrium. It is characterized in terms of what we call an equilibrium constant. What we call a KEQ value. And this can present itself in different ways. For example, if you're working with gas phase components, the KEQ could be a KC value. Or if you're working with the solutions of weak acids, it could be a Ka, an acid ionization constant, or weak bases, Kb, and salt ionizations, for example, KSPs. But they all mean essentially the same thing, and they define extent of reaction. Meaning that how long does it take for it to reach its point of equilibrium? Now, in working through some of these, we see how to calculate the equilibrium constant. Primarily, if we have a reactant to products, the K equilibrium constant is fundamentally defined as the concentration of the products divided by the concentration of the reactants raised to the coefficient power. Now, as long as the temperature doesn't change, you can expect the product concentration, reactant concentration ratio to be constant. Now, if you change the temperature, the equilibrium constant will change. However, it changes proportionally, and we'll get to that today and show you how that takes place. An equilibrium, once established, is reasonably stable unless one of three things happens. And this leads us into the topic that is the focal point of today, which we call LeChatelier's principle. Which fundamentally deals with shifting equilibriums. What causes an equilibrium to shift left or shift right? Now, we looked a little bit at this in terms of calculating a Q value and a K and comparing it to the equilibrium constant that's under certain conditions. And if we have a Q value calculated, now I want to do it K first, not Q. Start that over. I want to do KC, 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 QC 3 times. Now, this KC value is calculated products over reactants, and so is the QC value, calculated products over reactants, just like I've been explaining to you. But the issue with the QC value, it may not be at equilibrium. And because it's not equilibrium, it'll shift left or right based on the relationship between the equilibrium constants and whatever QC value is. Okay? If you make a calculation of QC and it's greater than KC, the way I've set this up, with the K first followed by the Q, then you can use the inequality as a pointer in the direction the reaction will shift. So in the textbooks will show Q first and then K. But if you switch those and use the inequality, it will shorten your memory effort and quickly tell you which way it's going to shift. However, The KC equals QC will certainly mean it's at equilibrium anyway. So you can shift left at equilibrium. Or shift right based on that relationship. Well, today we look at factors There are three primary factors which affect the shifting of an equilibrium. These include concentration effects, temperature effects, and a pressure volume effect. The way we will approach this in the context of shifting equilibriums is we'll take a typical reaction, A plus B, aqueous or gas phase or whatever, will be in starting with a dynamic equilibrium like this. And we'll look at it like it's sitting on a seesaw like this. And while it's level, it is, of course, at equilibrium. The issue is, how does changing concentrations on the reactant and product side affect the equilibrium balance? If we heat this or cool it, how does that affect the equilibrium balance? And if we change the volume, we will certainly change the pressure. This is a Boyle's law effect. So that you work with the empirical relationship, pressure proportional to 1 over volume, and increase volume, decrease pressure. Well, that's going to cause the equilibrium shift, or if you decrease volume, increase pressure, that's going to cause it to shift another direction. So we want to cover all of those issues. Okay, we want to start with concentration effects. And in the work that we're doing, we try to work with molar concentrations. Well, we can also work with moles, and in this context, because you're increasing or decreasing. But if we have an equilibrium, A plus B, and it's already in equilibrium with then what's going to happen is the equilibrium is going to tilt. You're going to have too much on this side right. So what you're looking at here is a system that's not at equilibrium if we put some extra A in. Now the thing that you have to, and that's easy to understand, people get that very quick, but to reestablish a new equilibrium, what must happen in the reaction that we're looking at? A and B must combine to make more AB. That's the issue in the recovery. Now, while it's in this tilted condition, we're not at equilibrium. We're in a Q value condition. So over here, this is a K value condition, if you will, and this is a Q value condition. And if it shifts to the right, what did our wants to shift right? We're looking for a KC greater than a QC. And using this, we want to calculate whatever this is and determine its shift back to the right. And in essence, it will reestablish a new equilibrium reestablish a new equilibrium with new values of A and B. An acidic buffer is prepared by using a weak electrolyte, weak acid, combined with the salt of the weak acid. The ratio of acid to salt and ions governs how stable that buffer is. An example is, say we have acetic acid, HOAC, that's the acetate, and we put that into a solution of sodium acetate right here. Okay, and if we have equal concentrations, say the concentration is 0.10 molar, and this one is 0.10 molar right here. We have what is known as a 50-50 buffer. Okay. The equilibrium of a buffer solution depends upon the equilibrium of the HOAC. Now, if we have HOAC in equilibrium with the OAC, well, I'll put the hydrogen first just for looks, OAC, then initially change in concentration at equilibrium, and we're going to change this buffer. Okay, this is the now condition as I put it in here. Then we're going to add some weights into the change issue and destroy the equilibrium, and then it's going to reestablish a new equilibrium with new concentrations like I showed you in the previous slide. So the way this one is set up, we have a 0.0 molar acetic acid combining with a 0.10 molar in acetate. Well, it'll have a very, very small concentration of acid in there. It's going to be 1.5 times 10 to the minus 5 molar. That's the concentration of acid, hydronium ion in that system. Now, as a buffer solution, the purpose of a buffer is to prevent large shifts of pH if an acid is added or if a base is added. Now, acids are added in terms of hydronium ions. So let's say in this case, we're going to add to this some extra acid. Well, this system has to remove that extra acid, and extra acid in will be like we're putting some extra H's in. Okay, so if we put some extra H's in, let's say we put a 0.01 molar extra right here in acid. Well, that destroys the equilibrium because our seesaw now is too heavy right here. Okay, so what has, you'll see the equilibrium tilt like that. Now, logically, you would have the reaction shift to the left, which it does. I'm not trying to throw any curves here. So what happens is the extra hydronium ion that we throw in combines with the acetate ion. See, this is an overload right here by that much, and produces more HOAC on this side. So while it starts out in the horizontal, it tilts like this, then the OAC and hydrogen begin to combine. Now when that happens, the concentrations go up over here and the concentrations go down over here, and we establish a new hydronium ion concentration like this. Okay, so if this buffer, now the purpose, remember what I said, it is to keep the pH from shifting, making wild shifts. So if we start combining H and OH right here, it's going to keep combining until you remove all of this. So what has to happen is I have to decrease this side right there, because you're going to combine those two, and it's going to shift to the left side, and it's going to increase by that much. That's what a shifting of equilibrium does. It creates a new equilibrium. So if I add these two together, the new equilibrium right here will be 0.11 molar in the acetic acid. Now look, this combination takes place to remove the extra, and it'll suck this out so fast you don't even know it was there. So we assume this is not even there to begin with. And so when the OAC and H combine to remove that extra acid, we're going to get a new hydronium ion concentration and a new effective pH. And it's going to shift a little bit to the acid range, but it ain't going to be much change. I'll show you. All right, this one right here subtracts, so 0.09 molar at the new equilibrium. The calculation of how much hydronium ion remains after we shift this around depends on the K value of this right here. The K value, the Ka value for acetic acid is 1.5 times 10 to the minus 5. For a 50-50 buffer, it is the hydronium ion concentration, is equal to products over reactants. Right here, HOAC. Now, the thing we don't know is right here.
Amber alert.
Somebody got an amber alert. Let's see if I'm live. Okay. We have the new concentrations of the acetate ion and the new concentration of the acid after the effective change takes place, after we shift the equilibrium and reestablish. The only unknown is the hydronium ion down here. So what we'll do is have 1.5 times 10 to the minus 5 equal the hydronium ion times the acetate, 0.09, divided by 0.11. And then we'll solve for the hydronium ion, 1.5 times 10 to the minus 5 times 0.11 divided by 0.09, and that'll give me a new molar concentration of the hydronium. If you can't see this, it says 1.83 times 10 to the minus 5 is our new hydronium ion concentration. Now I want to show you the effect of the buffer system after it undergoes the shift. Now we haven't gotten to all of this as yet, but pH by definition is the minus log of the hydronium ion concentration. The hydronium ion concentration before the extra acid was thrown in is the minus log of 1.5 times 10 to the minus 5. .82. After the hydronium ion concentration after is a minus log of the 1.8 times 10 to the minus 5 also, but it is increased slightly. When you add an acid to a buffer, it's going to shift a little bit to the acid. If you add a base to the buffer, it's going to shift a little bit to the base side. So we take 1.8 times 10 to the minus 5, take the log of that, and we get 4.75. So from 4.82 to 4.75, it ain't much. However, buffers don't prevent, please understand, prevent changes in pH. They only control the amount, and it shifts back and forth depending on whether you're adding acid or base. Now you could do this same thing. I can show you. What if you had the HOAC H plus plus OAC buffer? Initially, it's a 50-50. We can start 10 molar, 0.10 molar, and essentially it doesn't. 1.5 times 10 to the minus 5 is essentially a 0 right there anyway. What if we put in 0.01 hydroxide? Okay, so we add to this 0.01 molar in base, like that. Now the question is, how does that reaction, the buffer reaction, remove that OH? It removes the OH, the H by recombining with the acetate. If we added extra, it combined and shifted to the left. Okay, and it tilted like that and then tilted to the right. But if we put an OH in there, the OH has to remove that, or the hydronium ion has to remove the extra OH in there. And that's exactly what happens. What happens is the hydrogen will combine with the OH to produce the water. This is a very strong bond in there. So if you put a base in the presence of hydronium ions, hydrogen is going to hook up with the hydroxide very quickly. This is a strong bond here. And matter of fact, the concentrations are 10 to the minus 7, 10 to the minus 7 molar at 25 degrees C. That is next to nothing as far as water in itself ionizing. So if you took water and ionized it, pure glass of water, it's going to deliver only 10 to the minus 7 molar in each of those ions. That ain't much. So if you put an OH out by the hydrogen, it's going to hook up real quick and shift back to the OH, HOH, water. So taking this, what happens here, I'm going to put it right here. What happens right there is the hydrogen or hydronium ion reacts with the OH and causes one of the kids to leave the seesaw. So now on the seesaw, but here comes this OH and yanks one of the kids off the seesaw on this side. You see what's happening? It pulls off one of the hydrogens off of here. It's gone. There's nothing there. Well, then which way is it going to tilt? See what I'm telling you? It tilts toward this side, and it's going to shift back to the right. In the first case, it tilted to the other side because we added too much on the right side. And so they combine, and it tilts back. So this one right here is going to essentially take this out. Let me redraw that. You have, all right? Because you don't have as much hydrogen in it. You might as well say this doesn't even exist there. This is 10 to the minus 5 or something like that. But if you take the hydrogen off of the seesaw, it only has one way to tilt. So we have to break this down to replace this and create a new hydrogen. So what's going to happen in our little equilibrium table? This has got to go down and that's got to go up, and well, that goes back to a new hydrogen when you shift back in that direction. So if we work that out, HOAC equilibrium H plus plus OAC, CI changing CC at equilibrium, we started with a 0.01, 0.01, and that's effectively 0. 10 to the minus 5 is not enough make a big issue out of. But this time we put in OH's. So the OH has to remove this, causing this to go down 0.01 and this to go up by 0.01. And this time we'll have a 0.09 on that end of the equilibrium and a 0.11 on this end of the equilibrium, molar. And we get a new hydronium ion concentration. It's still doing essentially the same. Keep me honest. Well, the evaluation of the equilibrium is done the same way, products over reactants. Concentration of the products divided by the concentration of the reactants. Okay? Well, these are monoproducts, so you don't have any exponents to them. So Ka value for the acid, again, is H plus OAC minus over HOAC, like that. And the objective is, well, what is the new hydronium ion concentration? When we put in the extra base and the reaction itself is what shifts the pH or the reaction. So we now have, well, I just solved this for hydronium ion real quick, and we'll use that. Ka HOAC over OAC. We'll substitute the appropriate values, and we'll see what the new hydronium ion concentration is, and we'll calculate pH and see how it compared to before. And it'll shift to a more basic end in this case. Now that K value is a constant, and you look it up in the tables, and that'll be given. But the new acetic acid concentration in solution, you have to calculate. And it all comes out in moles per liter. So our new hydronium ion concentration is 1.23 times 10 to the minus 5. And using the definition of pH again, pH we started with originally, I'm trying to noted it, well, I'll just recalculate it, 1.5 times 10 to the minus 5. Now, this is old, you might say, original. And your pH new right now is minus log of 1.23 times 10 to the minus 5. And so we will go from, okay, so we started here and we threw in a base. Well, pH is going to go up per what we throw in, and the equilibrium is going to remove the excess base, but it's still going to shift slightly to the basic end. Okay. The second factor that affects an equilibrium is temperature effects. We'll use the same analogies and analysis in the seesaw effect, if you will, but this time you need to know the difference between the notations for endothermic and exothermic reactions. So that's where we'll start initially. Say you're given a reaction that's exothermic. The convention is to apply either a detached energy number or attach the energy number within the equation. If it is detached, A plus B goes to AB, you'll see a semicolon and a delta H of reaction that'll be like that. And it will be a number less than 0. Okay? Or you will see this, whatever the number is, attached to the product side of the reaction, indicating that it's a liberated value in terms of energy. It'll be A plus B goes to AB plus the delta H of the reaction. Now, this is on the product side, of the equation that's written, indicating the exothermic. I'll go ahead and put in the endothermics, and then we'll play with a few. Right here, it is this written the same way, except the H value, enthalpy value, or heat of reaction value, be greater than 0. In this case, we have A plus B in equilibrium with AB. You'll see a semicolon, and the delta H of reaction will be greater than 0. To incorporate the number in the equation, we'll put this one on the reactant side. Both of the notations, detached or included, are used on exams and in your notes and books that you'll be studying in the future. So you want to be comfortable with what the placement of the delta H value or the signage of the delta H value would mean in this case. Okay. I just grabbed a reaction at random out of the book. So they're all going to be treated the same way. Here is the oxidation of aluminum to produce aluminum oxide in this case. And here is a detached energy number. And the negative, 1676 kilojoules, indicates an exothermic reaction. If you wish to incorporate the number into the equation, you would place that on the product side. In that format, you do not include, obviously, and you know this, negative numbers when you write out a negative indicators when you write out a chemical equation. You can if you detach it in this context like that. Evaporation of water, very simple one, is in an endothermic reaction or boiling in H2O to a gas, which semicolon, delta H of this process is 44 kilojoules per mole. If I wanted to incorporate that into the equation, H2O liquid plus 44 kilojoules would go on the reactant side, and we'd have this equation in the symbology shown. So this is very important that you get this down early now, because when I do the I would just Now, what happens when we consider temperature factor and shifting of equilibrium? The temperature effect on equilibrium stability is that if you heat a reaction, the reaction will shift away from the heat enthalpy value. What? Okay. If I have an exothermic reaction, A plus B, set at equilibrium AB, included the delta H of reaction. Okay, now the reason you do it this way is so we can use the seesaw principle, if you will. Like this. Now, the case that I've just mentioned is what happens to the equilibrium when you heat that system. Okay? The way you analyze this is look at the delta H and play like it's a material object. And when you heat the system, you're adding material object to that side. So in essence, you heat this, heating, it will tilt like this. Okay. As a result, it's going to have to shift to the left. The opposite occurs if you cool it. It's like taking mass away from the delta H, if you will. And it's going to get lighter on this side and cause a tilt this way, and it will shift to the right. That happens for an exothermic reaction. It is opposite for an endothermic reaction. Thermic effect. If we use an endothermic, A plus B plus delta H of the reaction sets an equilibrium with AB, and ask ourselves, well, what happens? Now, of course, the fulcrum would be over here, but use your imagination a little bit here. So if we heat this, the issue is going to go into the reactant side. So we're going to be increasing the, so to speak, the mass of the reactant side. And so heating causes a tilt toward the reactant side, and the reaction will shift back to the right. Whereas if you cool the endothermic reaction, it will shift the opposite direction. Back in that, to reestablish a new equilibrium with new values. Okay, the last stress factor is pressure volume effects. If you have a reaction such as the ammonia synthesis, something like this, 3 moles of hydrogen, molecular hydrogen react, 1 mole of molecular nitrogen is in equilibrium with 2 moles of ammonia. All in the... Look at this reaction. What do you see? This represents 3 molar volumes. You recall a molar volume is the volume occupied by 1 mole of any gas. Now, we're not specifying temperatures, but 1 mole of any gas. Here is 1 molar volume. If you add those together, we have a total of 4 molar volumes. On the product side, this represents 2 molar volumes, or the total of that. Now, in working these equilibrium problems, this is what we call the low side, and this is what we call the high side. Of course, the high refers to the molar volume count, and the high side have 4, and the low side the lower molar volumes. Now, to understand what happens now is to change the pressure-volume relationship. Now, you recall from Boyle's law, pressure is inversely proportional to volume. It's the only empirical relationship that's inverse. Right here. So if I want an increased pressure, I would have to decrease volume, squeezing the balloon, so to speak. Or volume proportional to 1 over pressure. So if I wanted a higher pressure, I'd have to use a smaller volume. So Boyle's law prevails in this. Now, how do I apply this idea to the equilibrium? Well, if again, you have to take either one of them, volume or pressure. Let's say I increase pressure. Well, that's going to result in a decrease volume. If that happens with an equilibrium, a system in equilibrium, it will shift. Which side? To the low side. Increased pressure, decreased volume, shifts to lower VM side. We don't talk right and left in this context. We talk about who's got the most molar volumes in this one. So if I increase pressure, consequently, as a result of a decreased volume, I'm going to shift to the low side. So this would be shifting to the right. The opposite is true if I just reverse this. If I decrease pressure or increase volume, it's going to shift to the high side. So if I decrease pressure on this particular reactant, it's going to break this ammonia down and create more molecular hydrogen and nitrogen. You're given this equation, carbon monoxide reacting with the molecular hydrogen, producing the methanol. It's an exothermic reaction because of the negative, as we know. The question that I'm going to ask you is, how do we increase the yield of CH3OH be accomplished? Okay? So this is the essence. The consideration for concentration, temperature, and pressure is not just isolated within itself. All three of them can be used simultaneously to effectively produce a greater yield in a reaction process. When I ask for the increase in methanol in here, it's obviously we've got to do whatever we have to do to shift the equation right. That's the first thing you need to determine. Well, that's easy enough, okay, from the verbiage of the problem. Now, how about concentration effects? Okay, based on what you know right now, I needed to shift to the right, so what would have to happen to the equilibrium if placed on a seesaw? First, now don't miss this, first we have to disrupt the equilibrium by causing a tilt. It's no longer an equilibrium. And if we tilt it to the left, then it will shift to the right. We do not want to do whatever we need to do to cause a right tilt, because it shifts back to the left, and that violates the question that's being asked. So concentration effects would increase the feed, the reactant feed, the amounts of CO and hydrogen. One or both will cause the reaction to shift to a higher yield. Okay? Temperature effects. Well, we looked at this as an exothermic reaction. If I included that in the equation, would I put it on the right side or the left side? Anybody? Right side. Yeah. Okay, CO gas plus 2H2 gas at that. Now we try to decide whether we need to heat it or cool it. If I wanted to shift to the right, would I heat it? Would I heat this, anybody? If I heated it, which way would it tilt? It would tilt down this way and shift to the left, which would violate what the problem is asking. Standard temperature refers to 25 degrees Celsius. In the pressure volume considerations, would I run it at a higher pressure, lower volume, or lower pressure at a higher volume? Well, when we look at it, all of it's gas phase. I'm sorry, I forgot to put G in here. There we go. All of it's a gas phase reaction, everything in there. We want it to shift to the low side. Here is 2 molar volume, 3 molar volumes, and 1 molar volume. Okay? So if we wanted to shift to the right, I hope I got it all. 1, 2, 3 here. We need to shift to the right. So we need to, what? Increase pressure. Decrease volume.